and welcome to another Würth Elektronik webinar. My name is Zon and I will moderate this webinar today. The topic of today's webinar is how to deal with high inrush current and derating of connectors. The speaker of today is Götz Schattmann. Götz, hello.
Hi Silas and hi everyone outside there.
He will hold the presentation and also will answer your questions. Now, I wish an exciting webinar and have fun.
Yeah. Thank you, Silas, for the introduction, and I jump right into the middle so you can really see me. And also we jump right into the topic, and you see the title of today's meeting. And of course, we've been talking a lot about derating and the derating solution. And as you might guess, we will focus a little bit more on the inrush point, because this also belongs to the derating, but it can have some different approaches. Yeah? So here's the agenda, pretty short. So we do a little review about the derating, so everybody's on track, and then we're going to look about the inrush currents and how they affect maybe our derating. So we start with a summary, and here's a horror picture or horror show. And that's a truly image of a customer, not the customer itself, but his application, of course. And this customer decided to place this connector inside of a closed box, and they even took it with a higher current than allowed. And this was the result. As you can see, everything was melting down. The good point is we had no fire coming out of this, so at the end the connector interrupted everything, and everything was fine. But of course, as you can see, this is something that we really need to avoid. And so major point is, of course, to find the correct connector for our application. Here I have a little picture for you. We see some TBLs, for example, and as little information out of the data sheet, we can see here some environmental information, like the operating temperature should go up or could go up to a maximum of 105 degrees Celsius, of course. And we have a current rating of up to 20 amps. So now the question into the audience would be, what do you think? These 105 degrees, is this meant that you should not exceed the 20 amps at this point? So can I run the full 20 amps at 105 degrees or not? Or less? How much less? So that's the major question, what we're going to find out. Of course, behind of all that, we find a lot of standards, and some of the major standards are based on UL, the Underwriter Laboratories. And here we have the UL 1059, for example, for the TBL. We also have the UL 1977 related to data and power connectors. But you also have this on the international side, like the IEC 69477-1, also related to the TBLs. So you can see there are a lot of standards out there, and you, of course, have to decide which one is the appropriate one for you, concerning of the application that you want to run or use the connector inside. So a little review. I promised some formulas, but not too much. As everybody knows, a connector can also be seen just like a resistor. We don't have too much. We're not looking into alternate currents in high frequencies, so we can rely very much on the Ohm's law. So the resistor or the connector is just acting like a resistor. The best connector, of course, is the connector that you don't need. Of course, we want to sell some connectors. Yeah? So from time to time, you also need connectors that you can connect and disconnect your appliance or PCB. So that's the reason for that. What everybody knows as well is that we apply a current on a resistor. The resistor is going to heat up. The normal temperature of the resistor, here shown as T, is the temperature also of the surrounding, like the ambient temperature. Now, when it comes to an increase, then we talk about the delta T. So when the resistor is on current, then we have the final temperature, like the ambient temperature, plus the temperature rise here. So therefore, to find out a good derating or to specify the component itself, there is a so-called temperature rise test in place. That's why we show here that kind of climate chamber, and inside that climate chamber we can have the same environmental or a steady temperature around, and the thermocouple below is here on the very tip. It's a very small sensor for the temperature, because you should measure the temperature as near as possible to the real contact point of the connector. So there is also a test standard in place called the EIA 364-70. That is telling us you need to test at least 3 poles in respect of the UL 1059, and all the working of all 3 poles must be in series, and therefore the wires should be lead through all the poles of the connector, and then you power it up with the nominal power or nominal current. And when it's stable, you need to do at least 3 measurements every 5 minutes, and they should not vary more than 1 degree. And then we call that a stable system. So, yeah, at the hottest point, as I mentioned, we have two different standards in place. So, looking here for the UL, and temperature rise of 30 Kelvin is the maximum that is allowed for any component which is working under current. So, in Europe and all the IEC concerned countries, this can go a little bit higher than 45 degrees, yeah, and that is why we can have some different values, yeah. But we look closely on the UL type with a 30 Kelvin. Why Kelvin? Of course, it's about the same like Celsius, but if it comes to a difference like a delta, then we in physics we talk about kelvins, yeah, but the scale is exactly the same. So what happens if we have too high temperature? Everybody knows we create a heat development, as we can see, and heat development also means that we increase the corrosion speed. Every 10 degrees, we double the corrosion speed. And of course, this is nothing that we really want to have. Also the plastic aging that we can see here, it also looks like burned here or here, and we have some examples here what we did. So, of course, the plastic also is dying at too high temperatures. Then we also have the metal relaxation. That means if you have some spring force on your contact and the metal is going to relax, then the force applied to the pins is getting loose, and therefore we increase the contact resistance. And also, you know that with a higher contact resistance, we create more heat. And this is like something like a double circle here. Until we end up with pictures like this or like this. So everything is melting down. And this is definitely something that we need to avoid. So coming back to the same image, we have the resistor at ambient temperature. And by the Joule's effect, we have the temperature rise and the temperature of the component itself. So this is giving us the final temperature of the component. Yeah? Here's the way how to calculate delta T. The K is a constant concerning of the resistor, what type of resistor and what's its color and so on. Then we have the value of the resistor given in ohms normally. And then we have the current in the square. And this is important information, that the current is going into this formula in the square. So finally we see that here's the equation for the to compare, and what we see is that it's not absolutely equal, but roughly about the same. The reason is just that every conductor which is heated up creates a higher resistance than in a cold environment, so therefore it's roughly about the same. So let's look on a little board here, a little application. We see the ambient temperature is given at 50 degrees, and this component here, the connector that we're looking at, is specified for a maximum of 80 degrees. So we should never exceed this 80 degrees for the component. And yeah, the UL standard tells us we should never exceed the 30 Kelvin temperature rise while it's on work. So what happens if we power it up? Then you see that the current is, the temperature is rising here, and we have a little sort of a curve, and here we get in a stable state. So the system is no longer heating up, and as we can see here, the component itself is still below under 30 Kelvin. Temperature rise and everything is fine, normally. So the temperature here, rise here, took about 5 minutes, I guess. Yeah. So coming back to this formula, we see the total power. If you want to calculate it, it's the P given in the R by the I square. And yeah, at least what we want to point out with this is that the temperature rise is proportional to the square of the current. At the end, this means if you double the current, then you increase your temperature rise by 4 times. And this is important to understand. So as soon as a component heats up, hotter than the environment, then there's a exchange of the heat. So it's given the heat to the environment. This happens by convection, of course. So this is what we feel on your local heater when the warm air is going up, and this is warming all the surrounding. And this is exactly what happens here if we have a current flow here through the clamp. Therefore also it's pretty good idea to have large traces on your PCB. The higher or the bigger the surface is, the bigger is the surface that can dissipate the heat. So next point is conduction. And you can imagine if a current is flowing here, then heat is created here, and copper is a fairly good conductor for heat, and therefore with the wire you can draw out some heat off the clamp. Also via the pin, the heat is going into the PCB. However, FR4 material of your PCB is not really a good conductor for heat. Yeah? So last but not least, we have the radiation, what you feel when you come closer to a heat source or a fire or something like that. This is going in infrared light into the environment. And this is what happens anyway. Yeah? So there are also other possibilities to cool down your application. We handled this in our previous seminars about the derating. They are still online, and we have some application notes in place. It's called the ANE 006, for example, for the derating. Yeah? You can always find it on our webpage. So come back to this previous sample that we saw in the beginning. We have the TBL here, and we can see there's a maximum allowed of 105 degrees and a current rating of 20 amps. So how long can I apply these 20 amps? Still looking on the delta T, which is possible, maximum of 30 Kelvin, or the VDE type here. So at least this means all the way here, 100% on this scale, you can see the current on this way and the temperature of the component on this scale. So all the way down here, you see, we can run the full 20 amps. And now we have to choose the correct line. Component is specified for 105 degrees, which is the black constant line. So this is the line that we need to look at. So up to about this is about 75 degrees, something like that. So there, up to there, we can run the full 20 amps on this component. From that point, we need to decrease the current. And come back to the initial question, when the component is heated up to 105 degrees, which is here, your current is 0. Because if you apply more electricity, then you create more power, more heat, and this will bring you to that side of the line. And this is exactly what needs to be avoided, what's not allowed. Therefore, the answer is clear, and this is a misunderstanding in many circumstances, that there is the idea that this component could cover 20 amps at 105 degrees, but this is definitely not the case. So be aware of that. So far, you're on track about the derating. If you need to know more, you can refer to our previous seminars about the derating. Now we want to look into the inrush current. And of course, this affects the derating. Derating is looking on a stable system all the time. However, which system is really stable over its over all the time? This is not really the case. So here's an idea. If you look, we call it the good question, and I brought here a little component. Maybe my colleague can switch to that. So you can see here a little component, which is a TBL in the pitch of 254 millimeters, pretty tiny if you compare to my finger. And yeah, this is given with a current rating of 6 amps. I want to use that on my PCB, and it doesn't take too much space, and it's not very costly. So I'm lucky with that. Yeah? However, I found out that this little PCB should drive a motor. And I remember there was something like an inrush current for motors. So that has to run all over this little connector. Maybe that's a little bit of a problem. So I found out that this drive here I selected is taking about 6 times the current of the current rating. Yeah. So 6 by 6 is 36. So if I look to the range of our connectors, I find another one which is here possible for 57 amps. Yeah? And here's another one that I can show you just to compare it with this kind of just in size, that you see the difference. This is not even the same like this one with a 10.16 pitch. This is just a 9.62. And as you see, it's so large compared to the initial one. Yeah. So the good question here is, do I really need to use the big one, which is more expensive, which really needs so much more space on my PCB? It's killing my whole design. Yeah. So this is what we want to look inside. But how? What's the point here? Yeah? So of course there's a lot of applications out there, like you can see an e-scooter, and you can drive constantly, but you can also give gas and brake and gas and brake. Yeah? Or you have a standard motor which is driven, or it can also be an inductivity, or you can have a capacitor which in the DC acts like a shortcut in the first moment, or a tungsten lamp. Of course, most of you will have their lighting at home in LED technology, but tungsten, maybe in industrial fields, this is still active. Yeah? And of course, inductors are also concerned about this. So we were looking through all the standards, and we found the one for switches, really manual mechanical switches, which gives us an idea about the inrush currents that may occur. And here you can see about the motor drives. Yeah, they can go up to 6 times. Then for the next time, inductors also about 6 times. And here you see the tungsten lamp going up to 16 times, which is really huge, but of course on a short period of time. So also the capacitive discharging is possible when it comes to power supplies, DC converters, whatever. Yeah. So we did a little survey, we did a massive survey on the market, and we looked to so many different components. And out of the data of all these components, we created this kind of line or diagram. So you can see it's giving you a ratio about inrush current to the working voltage or working current. And on this scale you see the time it's taking, and this is the curve we ended up with. So what's telling us this? So come back to our application here with a little board. We see that the time, it took a certain time to heat up here and come to a stable moment. If we look very closely into a little part, like just in this corner, then we have the same line here, just another time. You see here it's in minutes, and here we go up to seconds. Yeah. So we ended up after 10 seconds, we ended up with an increase of only 5 kelvins. And this gives us a rough idea how to deal with that. So just to compare this again, we did another test with just a heated cable, and there's a TBL inside here, and we heated it up, and so this under working current here we received this line, so we're about 17-18 degrees, something like that, or Kelvin, because we're talking about the temperature rise only here. So still below 30, fairly below 30, everything's fine. Yeah? Now if we increase the current up to 8 amps, then we receive the brown line or orange line. So it's about over 30 Kelvin, obviously. So this is really not what we can handle. And then we increased further up to the gray line here, which is this one, and we ended up really, really far above. And this means, and this also can give us a proof of the formula that you saw before. I mentioned that if you increase the current by 2 times, then you increase the temperature rise by 4. So if you look here at 17-18 degrees, yeah, and this is about 63, 64, 65 degrees, something like that, yeah. This is about, not exactly, but about 4 times this, the temperature rise. Yeah? So this is giving us an exact proof. And of course, when we increase the current further and further, this line will go up even more quickly, and we had to stop also quickly not to burn our connector. So if we look to this, then we can see after 35 seconds here, we already got to the line of 30 Kelvin. And yeah, but at least we have a time frame here of this 35 seconds. Yeah? And applying this to another scale, this will give us a ratio about the working current versus the overcurrent. So we are on a ratio of 2.2. So for 35 seconds, we can apply 2.2 times the initial or the rated current to our component without exceeding the 30 Kelvin. Yeah? So this is what we brought here to this point. And if we do further measurements, then of course we can create this kind of line. And if we compare this line to the initial one that we taken from our market survey, we can see that this is pretty close. However, we're on the safe side. This means that the little gap that we have here between those 2 lines is giving us an extra margin, security margin. So this is the proof for us that we can work pretty well with the created line here. So this is all the components that we tested, and you can see the current ratio for everyone, starting from 1 up to 16 times the ratio. Of course, the time went down from 10 minutes in the beginning to 0.1 seconds, so 100 milliseconds in at a ratio of 16. So you can imagine how much work that is. So, and here you have some images about the components that we put on fire, not really, but that we put under current, and what the temperature rise was here. So to explain this graph, you can see that in the first 10 minutes, this is about 10 minutes here, in the first 10 minutes we raised, or we switched on this appliance, and then we got up to about still under 20 Kelvin of temperature rise. And if we would have driven that further, if we followed the line here, maybe at 23, 24, we would be in a stable situation. So still far below, under our 30 Kelvin margin. Yeah? And now we create additional inrush. So we gave here a little time frame, and then we started with some inrush peaks. And the most important point here is that you should give a certain time frame here. We choose about 5 minutes between the different peaks. And so in this example, we ended up here with a total temperature rise over the time from 5 Kelvin to 10 Kelvin, so at the end of only about 5 Kelvin. So this is something we can really go on to work with. Now if we come to look at the scale, and this is exactly the same scale again, but this is given you the time in 20 seconds here, while we look here on the milliseconds, and this is exactly, yeah, this area. Yeah? So if we look to this, we can go back, we can find out that within a short time frame, yeah, we can apply pretty much current on this component. Yeah? If we look, for example, to 0.3 seconds, then we can go about more than 8 times the ratio, yeah, and so on. And this is how we can find out where we are in the scale. So looking to the derating curve again, so base principle, of course, is that we never should exceed the 30 Kelvin in total. So we decided, so this is what you find here. If you, like I explained before, if you have a component which is usable up to 35 degrees, so the red curve here is in place, then you deduct 30 Kelvin, so this is about this point. So you end up at 55 degrees, where you need to cut down your current, not to come over this line. So then you're still on the safe side. This is about a stable system. Now we decided to cut the total temperature rise of delta T 30 Kelvin into 2 pieces like 15K each. So we can calculate to run our stable system. Here, once again, a stable system with only about applying 70% of the initial current. So we have a stable system, and then we still have enough space for the inrush current for the other 15 Kelvin that we can use for that. So this is the examples, and yeah, then we can really decide which ratio we can use for the current to compare, not to compare, to summarize the 15 Kelvin temperature rise of the stable system plus additional 15 Kelvin where we can play with our inrush. And of course, this is only an example, only a kind of attempt how you can go into this calculation. This formula, you saw that the components that we tested, there were some crimping components, there were some TBLs, but this does not apply to every component available on the market. Yeah? So you can find out inside of your application what is the current, the stable status, what is the when do you have your peaks of inrush, yeah? How is the behavior of your appliance, yeah? And the more data you have, the easier it is to do a good calculation. Otherwise, the other possibility is that you test over the time, yeah? And you try out trial and error, of course, yeah, until you come to the right point. But this is a possibility that we would like to show you here. Of course, you can also use the big clamp and you'll be safe for every time. And yeah, but with the lack of place on your PCB, of course. Yeah. And when we look to the components back that I showed you, maybe to the initial question, maybe this one could be the right one. Yeah? So it's right in between of this. So maybe you don't really need the full size one, but you come close with the other one without exceeding the rules. So I mentioned it's we measured with some terminal blocks, but you should always check with your connectors. And of course, we have everything for you collected in an application node. It's called ANE0015. You can also find it directly on our website, and we also will give it or spare it to you afterwards. And yeah, finally, it's important that you test your appliance. It's fully up to you. You're fully liable for that, not to exceed the standards. And yeah, therefore, what we can offer you from our side is that we help you examining your system and give you some hints in our local labs here in Europe is no problem. Maybe also in some spots in the US, yeah, or your local FAA can help you with that in an application lab. So thanks for now. This was it so far. So I'm open to your question. And maybe Silas, you want to come up, join me again?
Yeah, thank you, Götz, for your interesting presentation. Now we'll come to your questions. Before we start with the Q&A session, I will share you the handout from the presentation today. So now you can download it on the right side, and then we can start with the questions.
Did you see something coming in?
Yes. One question is already here. Yeah, then we can start with the first question. It was two questions in one. Approximately, how long does a typical connector take to reach steady state? Seconds, minutes, hours?
This is exactly what you saw in the curve. And this curve really needs to take into account what is your component, what's the environment, how it is connected, how big is the trace on your PCB, and so on. Yeah. So there's no rule by thumb that you can see, say, 5 minutes, 10 minutes, something. Yeah. Within a certain time frame of 15 minutes, yeah, everything should be in a stable state.
Okay, thank you. Then I see no other questions in the chat. Then we are finished for today. When you have questions, you can write into the chat, and then Götz will answer it via email in the next days. So now, thank you for joining. I hope you enjoyed it, and hopefully we see us
whenever
on our next.
Sorry to interrupt you. Yeah.
Yeah.
Whenever something comes into your mind, yeah, please raise your question, and yeah, we are lucky to answer all your questions.
Ah, I see. Two questions left.
Two more questions. Fine.
First question: where in the datasheet do we find a curve like the surge versus working radio? Yeah.
There is none like this in any data sheet. Yeah. Usually not. You find a derating curve, and so what you find in the beginning is that you can pull out these time frames. If you look very close to a very small time in the beginning of your temperature rise, then you can find out in what time frame you can reach a certain temperature. And if you refer to the information that we provide you with about the session today, then you can find the right path to calculate this to your concern to your particular component.
Thank you. Then next question.
By the way, additionally, before you start the question, the derating curves for all of our components are available. They're not online, but you can ask us for any component and we provide this information to you. And in very soon time, I think still within this year, hopefully, we will provide all the derating information for TBLs in our Red Expert tool that you can also find online. And from that point on, you can find it online as well.
Okay, then next question. Is there an equation you have found to estimate the temperature rise versus current over time?
Current over time, a formula. Yeah, we're still looking on the curve because you need to find out the different points. And of course, if you know the temperature rise of a single point, let's do it that way. You have a TBL, for example, and you apply a certain amount of current, and you measure the temperature rise that happens with that current until a stable state. From that point on, you can calculate the whole curve. And this curve that you can calculate is pretty close to what happens in reality. We've shown that in our previous derating seminars. They are online, you can check that. And it's very detailed described in there, so this is how you can find it out.
Okay, thank you. Then, no more question. Then, now we are finished for today. Thank you for joining. Thank you, Götz, for your interesting presentation.
Thanks for having me here.
And for all the answers. And yeah, hopefully you see us on our next webinar from Würth Elektronik. Good day and bye-bye.
Bye-bye.